Hello everyone, this is me again, Asam Helmi, a success partner with OBA Energy, and I will be your moderator in today's webinar. Today's webinar in the title of Gas Lift Theory, Operation and Design. I'd like to thank everyone joining us today. I see a lot of names of countries. Good evening from Egypt. As usual, in the start of any of OBA webinars, I give a short presentation, introduction about OBA and the services we provide. If you note that this is a free series of webinars. This webinar is number 67, so you can find all these webinars. The last 66 webinars are available on our YouTube channel. You can review all of them. Very interesting topics. And by the way, our instructor for today's webinar, this is not the first webinar for Engineer Ahmed Gaber. We have also some free webinars in production optimization and other analysis introduced by Engineer Ahmed. You can also find them on our YouTube channel. So I'd like to make sure that my voice is clear and that you see my screen also before starting this short presentation. So you can also type in the chat to make sure of this. Okay, thank you, Muhammad. So I will proceed with OBA upcoming services plan. This is our dashboard. You can find in this dashboard that we have already conducted more than 30 live courses in different topics. Each course is for 1 or 2 weeks. As I mentioned in the last couple of minutes, we have already conducted more than 65 free webinars and mentorship. We have also provided more than 34 mentorship programs for different clients from different locations around the world. As you see in the down side screen, the right side screen of my slide, you can see that we have reached almost every place worldwide. I'm not talking here about the number of attendees, but I'm talking that we reached this place. We have good retention rate for our customers. Each customer joining us in any of our services is joining us again and again. So this is the most important part of this presentation, which is the courses planned for this quarter during May and June. We have already started one of these 4 courses, which is water flooding design and optimization, which is started in 13th of May and is already running these days. Today is only the break day in this course. So this webinar is an introductory webinar for the next course, which is the gas lift theory, the operation and design, which is gonna start in the 27th of May and end by the 1st of June. 2 more courses during this wave of courses. One in the advanced integrated formation evaluation that will start in the 10th of June and end by the 15th of June. And the last course, which is a very interesting course, by the way, is advanced well intervention operations. This is the last course for this wave, which will start on the 24th of June and end by the 29th of June. As you can see on the screen that we have already planned for break days during these courses, which is highlighted in the black color here, which is usually Tuesdays, so that we conduct our free webinars during this day. You can scan this code to register in any of our courses, live courses, recorded courses, also the mentorship programs. I will also send the link to register in any of these courses in the chat area. You can find it in a minute. So the links to register in this wave of courses is in the chat area now. Actually, this is a list of some of the free courses that we have already conducted and are available as recording for your demanding. So courses in different softwares, the theory and application of using different softwares like PipeSim, TechLog, OFM, FreeCAD, Petrel, and many other interesting topics like perforation design, introduction to data analytics. You can find them all in this slide. Also, you can also register in these courses by filling in the same link that I sent in the chat 1 minute ago. You can also scan this QR code if you'd like to purchase any of these courses. And the more you purchase with us, the bigger the discount that we will be offering to you. Here is our mentorship program. This program is really different than having one week course. This mentorship program is designed by yourself, so you can choose your instructor and determine what would you like to learn. Your learning journey. This is on hours basis. So you choose the topic, you choose the instructor, everything on your design. So this is a special program if you'd like to join. I'd like also to encourage you all to visit our website. It's a lovely, interesting website. You can see here in a screenshot from the website. Also, this is another screenshot that shows that all the recording of these courses that I have just mentioned in the last slide are available on our website for your review, and if you would like to join any of these courses. We have already conducted some internship programs. These are ground events. Some of the students from Lebanon joined us here in Egypt for some training courses, and we also offered them with some interesting visits to some of the service companies here in Egypt, as well as some site visits to geological sites in Egypt. So before we go to our webinar today, I'd like also mention that it's very easy to be one of our ambassadors and enjoy all the discounts and offerings that we give to our ambassadors. You can be an ambassador just by joining us in any of these services, like live course, recorded course, in any of the mentorship programs or internship programs. Some few rules for this webinar before we start. I have muted you all. Sorry for this, but this is for the benefit for you all to get a clear understanding from today's webinar and not be interrupted by your colleagues. So the second one, if you have a question, please drop your question in the chat box. I will read your questions to Engineer Ahmed by the end of the webinar. Also, if you are joining us by a name like Galaxy, iPhone, or something that is not your real name, I'd like to encourage you to rename yourself, as we will be sending certificates of attendance in 1 week from today. Also, please don't open your camera. I will close it if you do this. So please keep your camera closed. This is everything for now. I'd like to thank you all, and time now to introduce our guest speaker for today's interesting webinar, Engineer Ahmed Gaber. Engineer Ahmed Gaber is a senior petroleum engineer in Gulf of Suez Petroleum Company with excellent technical skills and over 11 years of office and field experience. He is developing and maintaining integrated production system models. He is designing and optimizing artificial lift systems like gas lift and the ESP. He is providing short and medium-term production forecast. He's working with a team to generate and carry out an annual well surveillance plan and analyzing the resulting data. He is evaluating problematic wells for either rig or rigless intervention work. He is defining well functional specifications and well completion requirements, including perforation aspects. He initiated the well integrity policy to ensure the wells are producing safely and the intervention work are executed with perfect control and executing well integrity management plans. This is a short, brief introduction about Engineer Ahmed. This is a lot to tell. So, Engineer Ahmed, thank you for joining us today with this free webinar, and the mic is yours to start the webinar now. I will stop share and you can share your slide.
Hello, Isam. Hello, everyone. Thank you, Isam, for your introduction, and thank you all for attending today's webinar. And I hope it will be, inshallah, useful for all of us, bi'Iznillah. 1 minute, I will share my screen. So our topic today is gas lift theory, operations, and design. This is our agenda. We will go into an introduction about nodal analysis and artificial lift methods. Then we will go to gas lift theory, then types of the gas lift equipment, gas lift design, and we'll end with a case study showing troubleshooting. So in the beginning, let's all remind ourselves of our well system schematic. As we see, production started through the reservoir as fluid goes, oil and water and gas goes from the high pressure of the reservoir into the sand phase. Here, what we call the BWF or the bottom hole flowing pressure. Then it goes through the completion and up through the tubing into our wellhead, where we have our wellhead pressure, and up we have our chokes, and then our flow line ending with the separator or the tank or whatever our processing facilities. So in nodal analysis, we take a point and we study the relationship before this point and after this point, as we will see. In this case, in our case, if we have a nodal analysis here, before it, we have the inflow performance, which is the fluid movement across the reservoir. And as we understand, here we have our BWF, our bottom hole flowing pressure. Here we have our reservoir pressure, and the difference between them is the drawdown. And as the drawdown increase, then the rate increase. On the other hand, we have the fluid movement through the tubing up to the wellhead. And here we have the same BWF, bottom hole flowing pressure. And in order to increase the rate moving through the tubing, we will have to have higher BWF in order to overcome the frictional losses that increases with the increase of the rate. The upcoming slide showing exactly what I mean. Here we have this IBR curve, which is the relationship between the bottom hole flowing pressure and the flow rate. As we mentioned, as we move across the reservoir of the fluid, as the fluid moves across the reservoir, there must be higher pressure of the reservoir and lower pressure here, the BWF. The difference between both is the drawdown. So as the drawdown increase, as we see here, we start with BWF equal to the reservoir pressure, so no drawdown. As we decrease the BWF, then we increase the drawdown until we reach the maximum or the absolute open flow when the BWF equals 0, which is theoretically not applicable. And then we have another curve, which is the outflow, the relationship through this well bore, which is the relationship between the bottom hole flowing pressure and the rate. As we see, here, in order to go from here to up, we have two losses, the hydrostatic losses and the frictional losses. And as the rate increase, the frictional losses increase, and we come up with this curve. As we see, this is the outflow performance curve. So in order for the well to produce, there must be intersection between this curve and this curve. Intersection point is the point at which I produce. So if we have this curve for this well, this is our production rate, this intersection point. Here, it's our flow rate. And here, this is our BWF. This is the point at which we have the equilibrium between both the inflow and the outflow. So as I mentioned, in order to produce, I must have this intersection. What if we have that the reservoir pressure is low and we don't have this intersection, as in this case? As we see here, the reservoir pressure may be low, so this not start from here, starting from down here. And because of this, we don't have this intersection, which means the well is not be able to produce naturally. So in this case, we can use artificial lift methods. Artificial lift methods can be classified into two main methods. One method is adding energy downhole or transferring energy downhole into the fluid. And another method, what we will talk about today, the gas lift, is to decrease, as we will see later, the fluid density and the frictional losses through the well bore. So before we go to the next slide, I want to emphasize that we use artificial lifts in two scenarios. One scenario, as we see here, when the well dies, that the well cannot produce naturally. Another scenario, if we want to increase the rate of the well. For example, I'm producing a well and its rate like 200 barrel or 300 barrel. And for me, it's not economic. So I want to increase its rate. I want to produce it for 1,000 barrel or whatever or more. So in this case, I can also introduce an artificial lift method to increase my rate. This is a quick look at the most common artificial lift methods. As we see, this is the ESP. The ESP simply is a pump and motor downhole with electricity connected to it. And this motor moving the pump. Inside the pump, there is moving bars and other bars are in stationary case. So the movement introduce energy into the fluid that enter the pump through the pump intake and increases its energy and then its pressure. On the other hand, there is PCB pumps. These pumps is, as we see here in the photo, it's like a rotor also, helical shape, and a stator. And this rod is connected up to the surface. On the surface, we have moving engine that move this rod. And while it's it's also transfer energy into the fluid and make it have higher pressure to go up into the surface. While here we have the beam pump or the sucker rod pump. This is well common. And as we see here, it's like the surgeon. Like the surgeon, we have a plunger or a chamber that we suck the fluid into it, and then we discharge, we compress the fluid and give it pressure because the fluid is not compressible. So, and give it pressure and it's go up through valves inside this pump. Before I go to the gas lift, we have also these hydraulic pumps where we have power fluid. We inject the power fluid, it's go down with the produced fluid and mix and transmit a long part of its energy to the fluid. And our topic, our main method here is the gas lift. And we will go deep through the gas lift as we see now. So from this table, we understand that we have each artificial lift method, we have advantages and disadvantages. I will not go through each part for example, in the rod pump, as we see here, on the surface, it have big footprint. What I mean by footprint mean its equipment is big. So for example, I cannot use it on offshore platforms. ESP, for example, it need electricity source. ESP is sensitive to sand production. Beam pumps cannot handle high rates. PCB cannot go deep enough. Gas lift, for example, if the reservoir pressure is very low, then we cannot add the effect we want, so it may not produce. Also, hydraulic pump need the power fluid. So each artificial lift method has its application depending on our situation. And we will see an example when we go through the gas lift method. And here, this a pie chart I wanted to share with you, but bear in mind, it may not be updated because it has been like years ago. As we see, this was like 40% of the artificial lift is sucker rod. Why? Because it's cheap and easy to install and a lot of things and not needing high capital cost. Then the gas lift about 34%. Then the ESP is like 18%. And finally, the other PCB and other methods like jet pump, PCB and other methods. So now let's concentrate on our main topic or main artificial lift method for today. So what is gas lift method and what is the difference between gas lift and natural flow? As we see here, sorry, I tried to speak fast in the previous slides because it's only an introduction. And now I'll try to decrease my tone so we understand everything I'm talking about in the coming slides. As we see here, the fluid, here our perforations, and here our producing fluids. It goes through the tubing up, and then here the Christmas tree, and we have flow lines with the produced oil and gas. In gas lift, here what is added. We have injection gas here, and as we will see later, this injection gas is injected with high pressure. For example, to have the sense of numbers, in most cases in our wells, we have this wellhead pressure inside the tubing with about 150 psi, 250 psi, while this injection gas in the annulus here is going with like 1000 psi or 1200 psi. This injection gas is going into the annulus here into the annulus, and it's go inside this gas lift mandrel and gas lift valve, as we will see later. Here we have something we call gas lift mandrel or side pocket mandrel, this part of the tubing with increased size, and inside it we have the gas lift valve. So injection gas goes here inside this valve. The fluid is coming up here with gas liquid ratio, with the formation gas liquid ratio. Then we added the high pressure gas or injected gas here. So it mixes with this coming fluid. The effect of this mixing is to reduce to increase the gas liquid ratio of this mixture, which will decrease the hydrostatic and the frictional losses and decrease the pressure losses across the well bore as we go up. So, as we will see in the next slide. So, in the next slide, here we have advantages and we have disadvantages of the gas lift. The advantage is that it can handle high volume of the fluid. We produce with high liquid rates, 5,000, 6,000, 10,000, whatever. Also, it's not sensitive to sand and abrasive material because it's not having moving parts like ESP. Also, if we have gas, so we can make use of this gas. And as we will see later, these valves can be retrieved through slick line. On the other hand, we have some disadvantages of the gas. First of all, we must have source of gas present because as we will see, this is a continuous cycle. Also, we have high initial capital cost. Also, as I mentioned before, in some well, the reservoir pressure may be very low, that this gas lift method is not enough to produce the well. As we see, I mentioned in the previous slide that we have a disadvantage, the high capital cost of the equipment of the gas lift. Why? Because as we see, normally, let's take this well is producing. This well is producing oil and water and gas. It goes through a manifold, then it goes through a separator. Here in this separator, we have oil and gas separated. I mentioned that we have most of the time the wellhead pressure is low. And it's, for example, 150, 100 psi, 200 psi, whatever. And it goes into the separator. And normally the separator is very low pressure, like 60 or 70 psi. Then this gas, as I mentioned before, we need to inject gas with high pressure. So this gas must go into a compressor unit where this gas is compressed and its pressure is high. and then it goes into the injection manifold. This injection manifold will distribute gas into different wells, and each well will have a gas injection choke, which control the amount of gas that's injected into this well. Then it goes into the down into the well bore, and this cycle continues. So in this cycle, as we see, we need to separate oil from gas. Also, we need a compression facilities. Also, sometimes we need, for example, if the gas has a dehydration problem or something, we can need glycol unit or dehydration unit or injection of methanol or whatever. So as I mentioned here, this is pipelines and also compression station and facilities that need higher capital cost at the beginning. But once these capital costs are done and we have built this whole system, then the operating cost is not a big deal. The operating cost of the gas lift is low. And normally, most of the time, when we have offshore platforms, we use this artificial lift methods. It's the successful method because we don't have the problems of that, for example, long, big footprint as in the Sakar road, or we need electrical supply as in ESP, or power fluid as in hydraulic pump. So let's go deeper into our gas lift theory. As I mentioned, here we have our gas injection choke where we regulate the amount of injection gas going into the well. Here we have to understand two things. Here we have the upstream pressure, and here the gas downstream pressure. And then we go down into the well. We have a certain point where we inject through it. And this point, gas mix with the fluid coming from the reservoir, and the effect is decreasing the pressure losses across this well bore. So as we will see, the next slide showing this. For example, imagine I have a fluid, and this fluid is moving or producing with this gradient. Normally, the gradient of the fluid, oil and water, oil and gas is like 0.3, 0.35, something like this. So imagine this is the gradient of the fluid, the flowing fluid. So as we see, it will not continue till the top of the tubing or the wellhead. As I see, this is our case. At the injection point, I introduced gas into the system. The effect of this gas is increasing the gas liquid ratio, the overall gas liquid ratio. As we see here, in this part, cubic meter. Here at this point, we inject gas ratio, the total gas liquid ratio, and the effect rather than going through this direction, no, I have less pressure losses, which mean, as we see here, I can reach up to the wellhead. On another words, I could, because of the presence of injection gas, to have this drawdown. In the case I don't have injection gas, I must have a bottom hole flowing pressure with this value. But because I inject gas and I decreased the gradient above the point of injection, I could produce the same rate with lower BWF, so I can produce my well in this case. On another scenario, this is, for example, my natural flow. If another case, I have this well and I produce naturally with this rate. When I introduced the gas lift injection method, I could go into the right. I could go with more rate as I could decrease my bottom hole flowing pressure, as we see. I could decrease my bottom hole fluid pressure? Because the delta B required in this case is less than the normal, because I decreased the pressure losses here by increasing the gas liquid ratio. Why? Because gas liquid ratio, when I added it, it increased when gas is less ingredient or in density than oil and water. So it made my mixture less dense. So it decreases my hydrostatic pressure or my hydrostatic losses. As we know, when I flow through the well bore, I have two components of pressure losses, two main components, the hydrostatic losses and the frictional losses. So the introducing of these gas decrease the hydrostatic losses above the point of injection. So what types of gas lift installation we have? We have the continuous gas flow and we have the intermittent gas flow. So this is normally the continuous gas flow. As I mentioned before, we have our injection gas going with high pressure down into this injection valve, and it produce up the mixture of the fluid. Yani the formation here, the formation produce our formation fluid with its gas oil ratio. Then at this point, we introduce more gas. So we increased the gas liquid ratio starting from this point, and the whole mixture is going up. As we see here, if we go with a gauge inside the tubing, we have down here our bottom hole fluid pressure. Then we go up, as we see here, this is the gradient of the formation fluid. Then at the point, the operating point, or at the depth of the operating gas lift valve, here gas go inside the tubing. The effect is to increase the total gas liquid ratio, and the effect is to have gradient less than this gradient as we see here. And on the annulus side, if I go into the annulus side with gauge, we will see that I have high pressure gas, as I mentioned here. This is the downstream pressure here, and this is the wellhead pressure. So I have high pressure, and this is the gradient of the gas as I go down. It's very low gradient, 0.03 psi per foot, until I reach here. And for the gas to enter through the tubing, it must have higher pressure than the tubing, like 100 or 150 psi to enter into the tubing. So this is the constant flow or continuous gas lift method. Another method is the intermittent gas lift method. Here we use it when the reservoir pressure is very low, that it cannot, or the productivity index is very low, that it cannot produce continuously as in the previous case. So what's happening here? We have regulator or surface controller here. This controls the injection of the gas inside the annulus. And we have here this operating valve is closed, and it let some of the formation fluid to accumulate until we have an previously planned certain amount of liquid pressure. Then this valve is open and inject some amount of gas to lift this slug of fluid until it reach up, and then it's closed again, giving time to the reservoir to make a new slug. So again, we have these valves closed, giving time to the formation to build up some fluid slug. Then it's open, some injection gas is going in there to carry this or lighten this slug until it goes to the separator. Then it's closed and giving time to build up a new slug. As we see here in this and the previous, we have, although we are operating from only one valve, but we have other valves above it. And as we will come to it later, we have something we called unloading valves. So again, because this is very important and sometimes it makes a confusion. In gas lift, we have only one required operating point of injection. Above it, we have different valves, but these valves are here for certain purpose, as we will see later, for unloading, also here. So, as I mentioned, in this intermittent, we have advantages that we can use it in cases while we have very low reservoir pressure, but it causes sometimes, because as I mentioned, it goes closing up, and it's closed and then opening and closed, and we have slugging flow, which sometimes disturb our production facilities. Another division, or another way of dividing the types of gas lift, is according to the completion type. For example, the type I spoke about is this normal type tubing flow. I inject gas into the annulus and I produce through the tubing. Sometimes when we have a very large fluid rate, so sometimes this area, the area or the annular area, sometimes it's bigger than this tubing area. So sometimes I can inject through that tubing and produce through the annulus. So this is another way of different gas lift method according to the completion. So I mentioned before that the main thing, or the main concept in gas lift, that I increase the gas liquid ratio, which on the other hand decrease the overall pressure losses here. So one will ask me, so why not I increase the gas, or the amount of the gas, as much as I can? Here is not the case, because as we increase the gas liquid ratio more than a certain value, the effect here will be reversed. Like we will have more frictional losses, and at the end we will end up having, rather than decreasing the overall pressure losses across the wellbore, no, on the other hand, we will increase the pressure losses. So again, here we inject the gas. The gas, as we inject gas liquid ratio here increase. On the other hand, our hydrostatic pressure decrease. So as we increase the gas, this pressure losses will decrease. But up to a certain value, we will have more frictional losses due to high gas oil ratio. So this increase in the gas, in the frictional losses, will compensate the decrease in the hydrostatic losses, and we will end up starting to increase the pressure losses. And that's from this we can get our optimum gas injection rate, or gas liquid ratio. So this is what I wanted to mention. For example, here the well is dry. I am not using gas lift. Then I introduced or used gas lift. So as I injected more gas lift, I can go with the curves into this. I can go into this, like having more rate, until I reached a certain value of the injection gas, that when I increase the value of the injection gas, my rate will decrease, as we will see here. On another way, I can have a relation between the gas lift injection rate and the net oil production rate. As I increase the injection gas, it means I increase the gas lift or the gas liquid ratio, so I will have more fluid rate. As we see here, I increase the injection gas, I increase the gas liquid ratio above the point of injection, so I will have increase in the production rate until I reach a certain value. And at this certain value, when I increase the injection gas, I introduce more friction losses into the system, so my fluid rate will decrease, as we see here. So normally, when we design or try to choose the optimum injection gas rate, we try to use something in this interval. Like, for example, we choose, for example, here, I increase the injection gas but the increase on the liquid rate, like for example, here it's like plateau, like it's stable. Like I increase higher injection gas rate while the liquid rate rise is not high. So I use a certain point where I can have the highest available gas injection rate, and it gives me the highest liquid rate or net oil production rate. So we spoke about the theory and the different types of the gas lift. Now we will talk about the gas lift equipment in more details. We spoke, or we give a small summary about the surface facilities. Now I'm concerned more with the downhole part of the tubing. Normally, in the well completion of the gas lift, we have two things that we need to investigate: something called the side bucket mandrel and the valve itself. This will illustrate more what I mean. Here, this is the casing, and this is the tubing, and this is our bucker, and this is the annulus side. In the tubing, when we run downhole with gas lift, we have a part of the tubing with greater size here. It's called side bucket mandrel. This mandrel is designed so that I can put this injection valve inside it, and here through the annulus, I have ports here in this area. This gas goes inside these ports and then inside the valve itself, as we will see later, and goes into the tubing. So the communication between the annulus and the tubing here is through port here in this mandrel, and inside the valve itself, there is a hole here, and we will see it here more obvious. This is the side bucket mandrel. This is inside the tubing. The fluid is produced through this direction. And here, as we mentioned, here is the annulus. In the side bucket, we have a hole. This hole comes with another hole. This is the valve. This part is the valve. The valve having packing material here and here, so it isolates, it prevents the gas from going this way or going this way. The gas can only go through this way. So the gas can go through this way, down here, and it goes into the produced fluid through this, like as I say here, and goes down and into this direction. But as we will see later, in order to go this direction, here we have something we call the bellows, and we have here the something we call the port and this stem, and we need this stem to be open, so allow the gas to go this direction and goes and mix here with our fluid. So if I go in more detail, this is the valve. The valve, this is the valve from outside, as we see here, and this is inside. From the outside, the valve having like latching part, the part where we can latch the valve with our running or pulling tools. And then we have here two pucker elements. This pucker element, as I mentioned before, they set here into the mandrel to prevent the gas from going into this direction and force it to go only through the valve. And then inside the valve itself, we have this point where gas go from it. And we have something called reverse flow check valve. It's more obvious here, this check valve. This valve to prevent the fluid, if for example, for any reason, it's for safety, to prevent the fluid going from this direction into the annulus. We need only one direction from the gas to going from this direction into the tubing. So we put this check valve. In any case that this pressure here is higher than this pressure here, this valve will go in this direction and close this and prevent any fluid to going into this direction. So we not have only one type of these valves. No, as I mentioned, these valves we have different type of these valves according to its function and design. Normally, the available or the basic type of the valves that available in 1 and 1.5 inch sizes are dummy valves, something we called orifice valves, and unloading valves. I will go quickly through each type. Dummy valve, as we see, it's only a metal board. It doesn't have any like any holes or anything to inject gas through it. And we will understand later what is the scenarios or the cases I use it. Again, it's only dummy. It means only it's like a part of metal inside the mandrel, and it doesn't allow any gas to go inside or outside through this valve. It's like I closed the mandrel at this depth. Then we have another thing called this valve, the orifice valve. And from its name, it's orifice. Orifice is only holes here into the valve. It doesn't have dome or doesn't have springs or anything. It's only like an opening orifice, an opening valve. It's always open. This orifice allows the gas injection to go through the valve down into the well bore. And the last type is the operating valve. The operating valve, here it's more obvious. This is an operating valve. This operating valve have like dome or bellows and have stem, and this is close and open according to the pressure supplied to this valve. It's called operating valve. So this is the type or the main type of orifice valves that were known, something called square edges orifice and Venturi or Nova valve. And the name and function and the benefits, it based on the shape of the orifice itself. As we see here, this is the gas goes here from this into the valve and goes through this orifice into the tubing, while the Venturi have this different design, and this have more benefits than this in case of unstable cases or when we need a very low delta B across the valve. For me now, because we don't have more time to go deep into each valve, so for me the most important to know the names, and later you can search or you can know about it. And here we have this mandrel. As we see, each mandrel have its own engineering data with the pulling, the kickover tool, the running tool, the pulling tool, as we will see. This is the most important that I want to show regarding the side pocket mandrel. This side pocket because many of us can ask ourselves how I will retrieve this valve from here. Like I have this tubing and the valve here inside this part. It's aside on the side wall of the tubing. So how can I retrieve this valve and how can I run in this valve? This can be done with two things. Something called the orientic sleeve inside the mandrel itself, and something called the kickover tool. So what's happening that we have this valve, as we mentioned, the gas left goes here into the orifice in the valve and then go down here. Here we have the latch. We have something called kickover tool. This kickover tool is going with this side arm and into the valve, and we can run the valve down or we can pull the valve down. And this can be done with the help of the orientic sleeve. Like here, we go down with the kickover tool, and then we go up. When we go up, we here see something like like a metal or like a finger. This finger goes into the orientic sleeve. This finger here goes into the orientic sleeve, and it forces this arm to open into the side. Again, we have this orientic sleeve. We have like a finger. When we go up, with the kick over tool, it rotates and a finger goes here. This finger will force this arm to goes into the side pocket mandrel, and then we go down, and with jarring, we can set the valve, or on the other hand, we can latch with the valve and take it up and change it, whatever operation we need, like running down with a new valve, or pulling the valve and remove it, or whatever we want. So I mentioned again quickly, we have these three types of the valves. We have this dummy, and we have this orifice, and we have this what we call unloading valve or operating valve. So for this valve, it has we need to know some of its mechanic, when it's open and when it's closed, and what forces make it open and close. This is an operating or an unloading valve. As we see here, we have bellow pressure or dome pressure. We mentioned that the gas goes from the annulus into the port, into the valve, and it make force into the area between the stem and the bellows, while on the other hand, we have tubing pressure, which make an force or pressure into this area. And when we solve this equation, I don't want to take long time into this, because it's need long time to explain it. But the effect that we can solve this equation and get into the final equation, that here the pressure in the bellow is equal to the pressure in the casing, and A is the 1 minus the area of the port over the area of the bellow, while we have B plus tubing, and the tubing we have this factor B, and its area of the port over area of the bellow. On the other hand, in a simple way, in order for this valve to be open, here I have a certain bellow pressure that makes the valve close. On the other hand, I have two pressure that help me to open this valve, the casing pressure and the tubing pressure. But most of this force is coming from this casing pressure. For example, like 80 or 90% of the opening force is coming from this casing, and like 0.2, 10 or 20% is coming from this tubing pressure to open this valve. And this will lead us to the next thing, that we have two types of valves of these unloading valves. We have something called IPO, and we have another type of valve called PBO. So in continuous valve or continuous lift method, we have this IPO valve. Normally, we have the casing, it's working against the area between the bellow and the port. And we have the tubing, as we mentioned, working on this area. This is called injection operated gas lift valve. And this is mainly used in the continuous injection lift method. While we have another valve called BBO valve. In this scenario, it's different, like the arrangement or the schematic here is different from here. It's reverse. Like the casing is working against the stem, like here, while the tubing pressure is working against the area between the casing and the stem. The message here that in this scenario, most of the forces is produced to open the valve is impacted with the casing pressure, while here most of the forces required to open this valve is used from or coming from the tubing pressure. And it's normal, because in normal continuous, I have certain injection pressure and I open this valve and I want it open and I inject all the time. While here, I wanted to build up a certain fluid column, and when it's give high pressure, it will open this valve and it will let the injection gas come into this valve. Another method, something called proportional response gas lift valve, and it's also rather than here and here that the main force is coming from certain component. No, like it's divided between both the casing and the tubing. So I mentioned that we have only one operating from the beginning. I mentioned that we're having only one operating point in the gas lift injection. But in the same time, I mentioned that we have, yes, I mentioned that here we have only one operating point, but in the same time, we have other valves above it. Here, we have only one operating point, but in the same time, I have some valves above it, and also I may have some valves below it. So why is this? Why I have to introduce more valves than I need? Why not only like I have only one valve that I inject gas through it and have my production? This is because normally when I complete the well, I have this, as we see, I completed the well, I perforated, and then I killed the well. I have the fluid till the surface in the annulus side and in the tubing side. And if I go here in with a gauge, as we see here, the pressures, the tubing pressure and the casing pressure. If I go inside the tubing, I will having from the wellhead pressure here the gradient of the completion fluid inside the tubing and inside the annulus. And we will see that all the valves will be open because they have high hydrostatic pressure above them. So if I tried to inject gas, it cannot, I mentioned that here, for example, if I produce with wellhead pressure of 100 or 150 PSI, this injection gas pressure can be like 1,000, 1,200, or even 1,500. So I'm limited to the capacity or the performance of the compressors I have. So I cannot increase or use the pressure here more than a certain value. So if I inject gas, it will go according to its pressure and it will push this fluid into here and it will go into its maximum depth. Like here, this is the maximum depth, which is the size or the depth of the first valve, that with this injection, I can go if I have all here in the tubing fluid. Again, if I have, this is fluid, and I have like this, here I have fluid, and here I have fluid, completion fluid. With the injection gas pressure, I can go deep, the deepest or the maximum depth I can go to is here. So I must have an injection valve here in order to be able to carry this fluid. So I have injection valve here, and as I go, I push this fluid and it goes up. It goes up until I reach the fluid go inside the tubing. And as it go inside the tubing, as we see, it decreases the gradient here, less than the gradient here. And here the maximum injection gas I can reach. As more gas goes through this, as we see here, the gradient is decreased more, and I can push more fluid and I can go into the second valve until I have all this fluid going up through the tubing. And at this, after some time, this valve will be closed to allow all the injection gas to go into this valve. Like all the injection gas will go into the second valve, and part of the gas will push the fluid into go to the third valve. And when I reach the third valve, more gas will go into this third valve, and also gas going into the second valve, while the top valve is closed until the downstream decrease and this valve is closed, and I'm injecting from the third valve. So again, this is our case when I'm producing from a well. I already made a completion of the well. I have both completion fluid in the tubing and in the annulus. I want to inject and the gas continuously from the third valve, but with the injection gas pressure, I cannot go directly to the injection point or the operating injection point. So I need to have valves above to help me to reduce the pressure here in order for the gas to reach the third valve, which is the operating valve. So the function of the unloading valves is to help me to inject gases through them. And after I reach the lower valve, this upper valve will closed. As we see, this valve helped me to inject gas through it and left this column until I go into the second valve. And when I reach the second valve, this valve will start to close as we see here. And I continue producing from injecting from the second valve until I reach the third valve. And at the end, when I reach the third valve, and this is my operating point, then the upper two valves will be closed, which will make us understand why these two valves, I need them to be unloading valves. I need them to having certain values of closing and opening forces so that at a certain kissing pressure, they open, and on another certain kissing pressure, they are closed until I reach my operating valve. And this operating valve, it depends on my design. I can make it orifice, like only an opening, or I can make it operating also valve. And at the end, we have something we called here dummy valve or whiskey valve. It is like something like valve that we can use in the future when the reservoir pressure decreased. So I can go down and inject from this valve rather than this valve. So this will lead us to the most important step, which is gas left design. So what is gas left design? 1 minute, please, because of the azan. Hello, everyone. Now we will continue what we were speaking about. So as I mentioned, this is our unloading sequence. For example, in this example, we are operating or injecting gas through this valve, but we have two valves above it that we need to have as an unloading valves. So what is the design? The design, I need to put or to calculate the depths of these three valves. I need to identify where is my operating point, and on the same side, I need to know how many unloading valves I need and what is the below pressures for these valves. So this is design. I need to identify the depths of each valve, either it's unloading or operating. And on the other hand, I need to, regarding the unloading valve, I need to identify or calculate the bellows charged pressure. We have many methods for gas lift design, and there's a lot of inputs that we need. One of the well-known methods is the B minimum, B maximum method that I will use today with you. So how do we do our design? It starts with, first here, as we see, this is the pressure gradient curve. What does it mean? It means I'm producing with a certain rate. This certain rate, for example, like 1,000 barrel or 2,000 barrel with a certain gas liquid ratio. And then at certain depth, which is the injection point or the operating injection point, this gradient changes until I reach the tubing. On the other side, I have the available injection gas. As I mentioned, the ejection gas is injected with high pressure. So, 1 second. The injection gas is injected with high pressure, and this is our injection pressure. So I mentioned before this, and this is, as we see, we start from the wellhead pressure with a gradient of the completion fluid, because I have inside the well bore, when the well is killed, I have a completion fluid. These two curves, this curve and the injection pressure line, will match at a certain point. So this point is the maximum depth that I can go with my injection pressure, and I'll be able to inject into the tubing. And I take a safety factor of 30 to 50%, 30 to 50 PSI, and then this will be the depth of my first valve. So again, it all starts with drawing the pressure traverse curve of my designed rate and drawing the curve of, or the line of, the high pressure injection gas, and this is the gradient of the gas, and draw another line which is the completion fluid gradient starting from the wellhead pressure, and when they intersect, I take like 50 or 30 psi and I go up, and this is the depth of the first valve. Then same as this, I take a parallel line starting from this point, take a parallel line and take like 50 psi, and this will be my second depth. And then I calculate the casing pressure, the second casing pressure, by having an line drawing from the wellhead pressure into this point, and the intersection of this line, we have something called the BT maximum, and here we have the BT minimum. So we have our new casing pressure. Then same as this scenario, we go with another line parallel to the two previous line, which is the completion fluid, and we go also with 50 psi and draw a line, this line, and we have this value, the PT maximum, and we put it also into this equation, and we have PC2 until BC3, sorry, until I reach my last operating point. So again, because I know it's not very easy to understand, I draw my pressure traverse, I draw my casing pressure. Then what I want first to identify the depth of the first valve. Then I want to identify the depth of the second valve. So in order for the, as I mentioned before, the second valve, I need to make it open at a casing pressure less than the casing pressure of the first valve. Why? Because I want this valve, when it takes the injection gas, I want the above valve to be closed. Also, the same I wanted with the third valve. So this design, from this design, I satisfy or identify the depths of each valve. Also, I identify at each valve which is the B casing or the injection pressure that will open the valve. And I calculate, when I calculate this pressure, I calculate the difference between each casing pressure. For example, to make it clear, the first valve, for example, started here as 1000 psi injection pressure. Here, 1000. Then the second valve, I need opening pressure of 966. When I decreased below 966, for example, 950, I will see that the first valve will, when I decreased below or reached this value, 966, I will see that the first valve will be closed. Then, when I reached 946 as the third valve, this valve will open, and when I reached a pressure below it, the first two valves will be closed until I reached my operating point. So, generally, this is the output of the design. We will have like 1, 2, 3 valves, for example, here, and here we have the operating valve. And we have something we called whiskey valves. The meaning of whiskey valves is that it's valves that are not operating now, but with time, when the pressure decreased, I can use them. And for example, if they are dummy, I can put valves inside them, and I can change the upper valves with a slick line and use them as injection valves. Last thing I would like to share is the troubleshooting. One of the troubleshooting, what the means of troubleshooting? Troubleshooting is when the system is not working properly and I need to improve this system. So how to improve, how to look at this system? We have some well parameters, surface parameter, that I can look at them and know if the system is working properly or not. For example, the wellhead, if there's surge in the wellhead pressure, or if the wellhead temperature is not as normal. So from these things, I can understand if there is a problem in the gas lift. Another way, which is very important way, is gas lift survey. As we see here, gas lift survey, we go with pressure gauges, and above and below each valve, I record the pressure. And at the same time, I have temperature gauges that record the temperature before and below each valve. And also I have this injection pressure. And when I look into this gas lift survey, I can investigate it and evaluate if the system is okay or not. For example, here I can see that here we have a gradient. We have 0.4, 0.43, and then the gradient here started to decrease. So I understand from this gas lift survey that I have the point of injection is valve number 6. On the other hand, when I look into the temperature here, I can see that there's a cooling in front of this valve, which confirms that this is a valve that is taking this gas. But when I go up, I see also there is some cooling here, which suggests that there is some leaking through this valve. So I will recommend to remove this valve and change it with another valve and fixing or editing the bellows charge pressure. So thank you all for listening. I hope this was a useful webinar. I tried to give as much information as I can because gas lift is a great topic and it has a lot of things to do. And normally some of the topics that we cover today needs longer time to be covered. And I hope that you all enjoyed it. And I'm open for questions if you want.
Thank you so much, Engineer Ahmed, for this fruitful webinar. Thanks for your efforts. Everyone, please, I see some questions during the webinar. I'm sure that Engineer Ahmed answered some of them during the webinar as well. So please, for now, if you have a question, please send it in the chat box to read it to Engineer Ahmed so that he can answer your question. And also in the meanwhile, I have sent the feedback form link for this one of webinar in the chat box, and I'm sending it in again now. So please take a moment to fill in this form. I'm waiting for your questions, and please fill in the feedback form.
I see some that there's some questions here. I can go quickly through them.
Yes, I will read some of them. We have question from Muhammad Mansour, who is asking the depth of the top unloading valve depends on what? And he's asking what are the factors that determines the depth of the top unloading valve.
I don't, again, I can't hear you.
He is asking about the factors that affect the selection of the depth of the top unloading valve.
The factors that okay, the factors that needed to select the depth of the first unloading valve. Okay, as we see here, what we suggest at the beginning, we suggest the worst case. What is the worst case? The worst case that we have fluid like this. This is our worst case, that we have fluid into the well here, into the surface. Okay, for example, we kill the well and we have fluid up to here. But for example, if there is a case that the wellhead or the depth of the fluid is not here, what it's here or down, for sure, at this case we don't need the depth of the valve to be here, but we make the design for the worst case. Okay, we make the design for the worst case. So the worst case here that I have the fluid at this depth. So I started, for example, if I came with the 1 second with the design here, I started here that I have this completion fluid, this gradient. I have this gradient from the here, and I started like this. But what if, for example, I have it here or down? I can start with this. But the problem, I also always have this danger of having the valve deep, and then I have this fluid level up, and I start to inject, and the gas cannot go deeper. So at this time, I will have only one solution, that to go with coil or to go with nitrogen and try to unloading the well. So this is the risk of it.
Okay, Engineer Ahmed, the next question.
So the one who asked it, please reply if it's clear or not. So if it's not clear, I can like try to illustrate it or explain it again.
So okay, Muhammad Mansour, you can raise your hand if you would like to speak. I would unmute you. So if you would like to speak for more clarification or more question, you can raise your hand.
So you are welcome all for your. I'm happy for hearing that you enjoyed this webinar. So I'm very glad to read it from you. Thank you all, and really it was a great honor for me to present to you all.
Yes. Engineer Ahmed, is it okay to share these slides with our audience?
No problem. I can share it. No problem.
Okay, so someone is asking about this. It will be shared through our LinkedIn channel soon. Also, someone was requesting to record this webinar. As I mentioned, it will be available just after we finish on YouTube. It will be available to
Thank
review
you.
it. So no need to record the session. So we have another questions also. How many valves we must have in the well compilation about gas lift? I know that you answered this during the webinar. If you'd like to add more comment to this, it would be good.
So it depends. Yani in some cases you may have one or two valve. It depends on many things. It depends on what is the depth of the well. It depends of how much the rate of the well. It depends on the reservoir pressure. So it depends on many things. So in some wells we have 3 valves. In other wells we have 10 valves. So it depends on case by case. It's not having like a certain number that is the normal number of valves. Yeah.
Okay, thank you. What types of software that we use for gas lift design?
For me, I can use 2 things. Yeah, for me, normally I use if there's Excel sheets that having this correlations and input data, and also I can use for me I use Prosper. Yeah, normally I did it with these 2 things, with Prosper and with Excel sheets that having the correlations and the equations for gas lift. And for service companies, I think they have their own software for gas lift design. And I didn't try it on PipeSim, but I think also PipeSim we can do it. Yeah.
Yeah,
But we will
sure.
see that most of them, yani, yani, I made it before. I made it using Prosper and I made it using Excel sheet, and both were the same. There's no difference. Yeah.
So for people asking about the design of this gas lift, I know it's a little bit complicated design. So I'm not sure that it's the time to give more details about the design. So I'd like to encourage you to register in the course to know more about every detail of the course. So any other question, guys? Please don't forget to fill in the feedback form. I will send it again to the chat.
Excuse me, there is someone, Dimitri, was asking about. Yes, and previously the ESP, and we use also ESP in our offshore. I didn't say that ESP cannot be used in offshore. ESP is using in offshore, but it's it's have a challenges. Like for example, you have to have this cable from the onshore or from the VSD into the platform. We in our company, for example, having a lot of problem that sometimes ships or sometimes having problem to this cable, and from time to time we change it. And also in some cases you have this ESP plus gas lift, like you go with ESP like a primary injection or a primary artificial lift, and you can use gas lift as a secondary in case that there's a failure of the ESP. You can go with the gas lift with it. So in the same completion you can do it, yani, and it's very interesting as you mentioned. And we have yani, like 6 or I think 6 or 7 wells that are ESP in our company offshore. This is was to Dimitri. Yeah.
Yes, yes. ESP is common in offshore, like in shore. But the combination of gas lift and ESP here in Egypt, I don't think it's a lot of applications here.
Yes.
Yes. So guys, this is the end of our webinar. We already beyond the time. So thank you for joining us for today. And I would like to thank also Engineer Ahmed for taking the time to share his experience with us. Also, I'd like to encourage you all to follow us on social media. We will continue to share this type of free webinars with you all. So see you all in the next webinar. Bye.
Thank you.